the dynamic, for example, solving the overall dynamic behavior of my vehicle to compute or to solve the vertical dynamics or vertical dynamic response on the driver position. Okay. So as I said, this is extremely easy to be implemented in MATLAB Simulink. And this is the first step for the dynamic analysis or for the dynamic design of a vehicle from the comfort point of view. Okay, and as I think have already used all the time, I will finalize my presentation here. So if you have any doubt, any question, anything you want to comment, I will be really happy to answer before the break. Mr. Muhammad Al-Mahali, I think wants to.
Dr. Muhammad Najari, please go ahead.
Yes, please. Thank you very much. This is Dr. Muhammad Al-Majali from Mota University. I always find the vibration topic is very interesting. And I would like to thank you for this comprehensive presentation regarding this. Actually, I have some comments and questions in this regard, and I will say it once, and if you can respond later, it's up to you. Usually, the sources for the vibration is coming from the dynamic or rotation components, such as the engine or the motors. So we usually refer the low or medium or high frequency of vibration based on the RPM of such components. This is the first thing. The second thing is regarding the direction of the vibration. We usually refer it to a vertical or a lateral vibration based on the axis that the vibration is on. My question is also regarding your presentation is basically talking about how you are going to do a model for making the vehicle comfort. But as you know, this program is directed to the technicians or engineers who is going to maintain the vehicle. So how can make the test driver to see or to test if there is a vibration in the car and how he can measure it in IPS, in inch per second, or in any way, and how he is going to tune such vibration. So which component is going to replace based on the feeling, human body, or based on the frequency that he sends. So this is actually what we need to do it in the vehicle. How can the driver feel if there is a vibration, how he is going to measure it, how he is going to tune it to replace or change any parts. I would like maybe later on, if you think about it, to give another representation about this. This is my comments and questions. Sorry for the long saying.
Great. Thank you very much. Fully understood. I can give you answer now or later, whatever Sarah, the moderator, wants. So whatever you told me, I can do it now or later, whatever.
Maybe we can make it at the end of our presentation, so we can collect all the questions and
Good.
Yeah, perfect.
Good. Thank you. Ahmad Qashia, please, if you have any question.
Professor Ahmad Qashia, please. Then Mr. John, please, you can complete.
Good.
Okay. My question
yes,
about
yes.
my question about vibration dose value, a comparison between motor excitation and road excitation. This is the first question. Another one about is there any threshold value for this vibration dose value? And let's say to measure the comfort while driving the vehicle. The last question about the critical value of damping. As you know, in general, a driver with the passengers, the mass of the vehicle varies as the number of passengers increases. In this case, you know, the damping ratio will change also. You know, the system may transfer from over-damped system to critically damped system to under-damped system. What about the analysis and the vibration dose value also compared with the damping ratio of the vehicle or the dynamical system of the vehicle? Thank you very much.
Thank you very much. Understood.
So yes, please, Mr. John, you can complete your presentation, and we can answer all the questions at the end of our workshop.
Okay. Okay, good. So okay, so let's go for the second part of the presentation if you want. I don't know if you want to make a small break or should I continue directly? I think I should continue directly, right? So, okay, let's put this into practice. Okay, let's figure out how can we put this into practice. Okay, maybe I will. Okay, we need, let's say, the idea or the key concept here is. I fully understood the question that the program is for technicians, is for
yeah. If you allow me.
Yes.
Excuse me, John. Sir Ahmed Qaisiya, I would prefer if you can now give us the answer, since now we recognize the questions, and other colleagues who have questions, they can ask after you finish your presentation.
Okay. Okay.
But
good.
if we can hear from you now and answer for these two questions.
Great. I will go for them. So the first question was regarding that the excitation of the engine is usually measured in terms of the RPM of the engine. Here, the key point is that the comfort is filled between 0 and 10 Hertz. The key point of comfort, the overall of the comfort we perceive, it's between 0 and 10 Hertz. The excitation coming from the engine, it's above this. If we want to consider the impact of a rotating element on comfort, this component, the frequency of this component will be around 40, 35, 45 Hertz. So it's a frequency with low impact on comfort. I don't want to say that it has no impact on comfort. What I want to say, it has low impact on comfort. And linked to the comment on vertical and lateral, this is the key point. If I'm facing the camera, let's say X axis will be through the camera, Y axis will be transfer direction, and vert and set will be the vertical. So the key point is the rigid body motion of the car body on the suspension. Okay, so the vertical movement of the rigid body motion of the car, this is set, this is theta y, this is theta x, and this is yaw, theta set, will have the higher impact on comfort. For example, if I want to consider the impact of the transmission of the vehicle on the comfort, for sure I can do it, and for sure it will be a function of the RPM of the shaft. Those RPM we will translate them into Hertz, and that will be the frequency of the excitation we are going to use. The amplitude of the forces can be computed from the dynamic behavior of the eccentricity of the axis. Your second part of the question was, this is for technicians. This is for technicians. How are they going to be able to identify which is the problem? And the answer to that question is it's more complicated. It's more complicated. It's not a really easy task. But my practical example for this second part of the workshop is trying to put some light on that. What we need to do is we need to place an accelerometer in a point, perform a defined analysis, and obtain a spectra or spectra of that vibration. Let's see the frequency components of that vibration. If we compare the spectra of the comfort car or the healthy car with the spectra of the all or non-healthy car, we will be able to see which peaks are not in place. So therefore we could identify if we have a problem on a bearing, or we have a problem on a damper, or we have a problem in other component. I fully assume it's not an easy task. It's extremely complicated, but noise and vibration is one of the key points in electric vehicles. So a lot of complaints from clients come from noises and vibrations perceived in the electric car that in an internal combustion engine won't be a problem. Regarding the second question, regarding the vibration dose value, here you said if is there any threshold for the vibration dose value? What we need to understand is that the longer the signal, the lower the comfort. So the vibration dose value, it's a way of trying to make comparable a short signal with a really long signal. If, for example, I measure a phenomena that lasts 2 seconds, the RMS value of that phenomena will be less than a phenomena, for example, lasting for a higher period of time. So the vibration dose value, which give us, it's the ability to compare, or the capability to compare 2 different signals. I will change your question, and the thing is that we have the threshold in the human body. The human body won't be able to perceive accelerations below 0.05 meters per second square. It also depends on the axis. The perception in Z is not the same as the perception in X, but let's say that broadly speaking, the human body is not able to perceive vibrations below 0.05 meters per second. So if we can take our system below this level, we can consider that our system is quiet or not vibrating. And the last part of your question, this is the key point. This is the key point, and this is extremely important. Let me take the example of an internal combustion engine. Let me take an example of a minibus. Okay. Let's assume my family is a big family, and I have a vehicle with 8 places. If I drive the vehicle myself, the mass of the vehicle, it's extremely different if I drive my vehicle with my whole family, with the whole luggage, and with the tank full of gas. So here, the natural frequencies of the vehicle and the comfort of the vehicle and the way it behaves in a turn, the understeer behavior or oversteer behavior will be dramatically affected by that but that change in the mass distribution. So, which is the key point here from the designer point of view or from the vehicle design point of view? Once we are designing the vehicle, or once we are, let's say, designing the vehicle, we need to evaluate which is going to be the range where the vehicle is going to work. Okay, so from the lowest mass it can have on road conditions to the higher mass it can have on road conditions. And if I do this, I will be able to evaluate the change in the dynamic behavior of the system. So regarding the critical damping, as you mentioned, on the one hand, the natural frequency of the vehicle is going to change, but also the critical damping of the system is going to change. So the overall dynamic behavior of the vehicle will change if I load the vehicle or unload the vehicle. I don't know if I've given answer to your questions, or you want to add more comments.
No, thank you very much. Everything is clear now. Thank you.
Great. Thank you very much for your questions. Good. So I'll go for a brief example, and I want to show how can we do this in practice. Okay, how can we do this in practice? So as you see on my screen, as you see here, I'm using a software called CarMaker. Okay, CarMaker, it's a parametric software. What does it mean? It means that I can just give values to the parameters defining the car. Okay, here we have a lamp parameter system. Okay, a system characterized by properties that we can translate into a parameterized software as CarMaker. In CarMaker, what we have, for example, it's the vehicle we can consider, and this vehicle we want to consider, it's described as a lumped parameter system where the only thing I have to do is to define, for example, the mass, stiffness, and damping properties of my vehicle. Okay, so for example, here we are going to simulate a family minibus, a Mercedes V class. And for example, what do I need to do for developing my model? Okay, let's use the overall mass of the vehicle. Let's compute the inertia properties of the vehicle, and let's locate the center of masses of the vehicle. Once I've done that, I can add all the masses below the suspension. All the masses below the suspension, we have here the rotating masses. This is the wheel from left, wheel from right. These are the rotating masses, and these are the non-rotating masses, the suspension arms and brakes and so on. That it's exactly the same concept. The only thing I need to do is to place the mass properties and the inertia properties regarding the coordinate system of the vehicle. So regarding the coordinate system of my vehicle, I can place the wheel, or I can place the mass of the vehicle, or other elements. So also I can identify where the jack, this is the free height of my vehicle, is placed. Okay, so I can check where each of the masses of my vehicle is respect to a known system of coordinates. Okay, The next elements are the engine modes. And the engine modes, once again, I'm giving the mass of my engine, the inertia properties of my engine, and from let me go slightly back to my prior presentation, here. Sorry. Here. Here. So in my prior presentation, we said that the engine modes can be computed or characterized using this kind of lumped parameter systems. So the only thing I can do, or I have to do, is to develop a model to identify which are the stiffness and damping of my engine modes in X, Y, Z, and also regarding the other two torsional degrees of freedom. Regarding the suspension, it's exactly the same concept. It's exactly the same concept. If I have quantified the stiffness of my suspension, the stiffness, or sorry, the C parameter of my damper in bound and rebound, the value of the anti-roll bar, the value of the anti-roll bar, and also if I want to introduce the kinematics of the suspension, but always just considering lumped masses, lumped springs, and coordinate systems. Regarding steering, I can also define which is the steering gear ratio. Regarding tires, I have a set of tires I can use for my system. I will show you this here. For example, I will go for 30, 245, 45, 245, 45, 16. Okay. So here, if I select this, if I select these tires, as you can see, these tires will give me the vertical force the tire can hold and the slip angle the tire can work. So here, this information of the tires, it's exactly the information of the tires I can have here, and the brake distribution and the powertrain. Here in the powertrain, you can go for, in this software, you can go for any kind of configuration of powertrain, from internal combustion engines to hybrid to whatever, or to pure electrical. In this pure electrical, you have several combinations regarding, for example, one electric engine in the front driving, one electric engine in the front axle, or two electric engines, one for each wheel on the front, or two electric engines for the front axle and rear axle. This is, you can go for any architecture of drivetrain. Once you have decided the architecture of your drivetrain, you just have to define which are going to be the power and torque. This is the torque versus rotational speed of the engine in motor mode, or of the engine in generator mode. Same for the driveline. You can define if you have the engine on the front with an axle taking the power to the front wheels, or an axle taking the powers to the rear wheels, or whatever the combination you need to design, and also the aerodynamics the aerodynamics acting on the vehicle. Okay, so once you have designed your vehicle, you need to design which is the road where you are going to drive your vehicle. Okay, so for example, what I have here, it's a small experiment. I have prepared a small experiment of the van going through a bump. Sorry for that. Let's stop the simulation. Let's restart the simulation. I think I have some connection problems. Let me reload it again. Okay, direct problems, as you know. I prepare. Okay, so let's let me close this and open it again, because I think I have some connection problems with my license. Okay, there it goes. Okay, so this will give us the opportunity to analyze the dynamic behavior of the system. Okay, so for example, in this experiment, as you can see, as we have changed the position of the wheels to improve the stability of the vehicle, we have some, let's say, some graphic problems. But the key point of the experiment is here. For example, you can see the vertical forces, the traction forces, and the lateral forces. So while we are going through the bump, we can see not only what is happening on the wheels of the vehicle, but we could also obtain any information we want from the vehicle. Okay, so for example, I can look for the vertical forces in the front right wheel, the vertical forces in the rear right wheel, and for example, let's say that I can go for the vertical acceleration of the car. So if I retake my example again, if I run my simulation again, I can see how the vehicle is going through the bump. Okay, how the vehicle is going through the bump, and how the vertical forces are acting on the center of gravity of my vehicle. So identification of the frequency components of this signal will give me a clear idea of the comfort of the vehicle. Will give me an idea of if the vehicle is behaving as it should be behaving or not. So the idea here, or the situation here, is that we can define, or we can prepare any kind of test to evaluate how the vehicle is working. So we can define any kind of real world road scenarios, or any kind of circuit scenarios to, and sorry, my mistake, to analyze, for example, how is the dynamic behavior of the system. So by means of the infinite circle, for example, we can analyze, or we can evaluate the understeer or oversteer behavior of the vehicle. We can analyze, or we can design or improve the dynamic behavior of the vehicle by defining whatever the dynamic test we want to achieve. Okay, so here, by means of simulating the dynamic, the infinite circle, the kind of information we can obtain is, sorry, let's go back to this view. It's, for example, the lateral behavior of the vehicle. So here, for example, let's go for in the car. Let's go for example, for the lateral acceleration, and for example, let's go for the slip angle in the front right and in the rear right, for example, and let's go for the simulation again. So here, what we can do is define as many standardized tests as we want to characterize the, let's say, the healthy behavior of the vehicle. So this will give us the expected behavior of the vehicle, so we can compare this healthy expected behavior of the vehicle with any real world measured behavior on the problematic vehicle. Okay, so here, for example, as you can see, what we are achieving is the limit of the lateral traction of the vehicle, identified by this change, this abrupt change in the slip angle of the vehicle. Okay, so I think this is all from my side. Thank you very much to you all for your kind attention, and for taking the time for attending this presentation, for attending this workshop. I really hope it's worth the time for you. And thank you very much to you all for your time, for your questions, and for your interest. Any question, any comments, anything you may have now or later or in a week, you are always welcome to address me, to contact me, and to have a chat or a video call or email or whatever to clarify any question or comments you may have. So thank you very much for your attention.
Thank you, Mr. John Garcia, or muchas gracias.
Thank you very much.
For your great efforts and for your valuable time that you have spent with us today. Impressive presentations and impressive work. Thank you. So for the audience, please, anyone have a question, please raise your hand, or you can just open your mic and go on with your question. We are now opening the discussion and questions. So please go ahead.
I have one question only.
Yes, please.
Thank you very much. Thank you for your presentation. I want to ask you if there any chance to model the road condition.
Yes.
Not only simulation of the vehicle dynamics. I mean, you know, sometimes if we have rain, if we have snow on the road, this will affect the traction forces on the vehicle and also will affect the whole dynamical behavior.
Yes, yes, of course it can be done, and you can I'll give two answers to your questions regarding road conditions, regarding the roughness of the condition. You can model it by using 3D conventional design softwares. So for example, the roads I have used on this presentation are perfectly smooth roads, but you can draw or you can design any road you want to evaluate the effect of roughness in the dynamic of the vehicle. And of course, you can include traffic conditions. You can include rain, you can include snow, you can include other vehicles, you can include other situations in the simulations to be considered for the dynamic response of the car.
Okay, thank you.
Thank you very much.
Thank you, Professor Ahmed, for your question. Any other questions, please go ahead. Yes, we have Professor Muhammad Al-Majali. Please, Professor Muhammad.
Yes, it is allowed for me to ask another question, or?
Of course, you have.
Okay. Actually, he answered the question which was in my mind, but I just want to ask another question regarding the braking system. We usually neglect the vibration coming from the braking system, especially if you know the pads or anywhere in this system, or sometimes if there is an air bubbles inside the hydraulic system, this sometimes makes some vibration, especially when you are applying the brakes. Is this considered in this situation or not, or it's also negligible?
Thank you very much for the question. In my simulation has not been considered. But let me share my screens again in really quick. Here in the brake system, you can just define which is going to be the pressure distribution. Okay, you can just, let's say, model the healthy system. But what you can do if you want to include this kind of excitations you mentioned, you can do that by including external forces in the suspension. So here, by calculating outside of this software the forces created by any kind of phenomena you can model or you can simulate, you could include these forces to be considered during the simulation.
Okay, thank you.
Thank you very much.
Thank you, Professor Ahmed. Muhammad, any other questions? Please go ahead, open your mic or raise your hand. Please feel free to ask any question you have in your mind. أي أسئلة؟ Okay, then maybe we
I
have
can
a
ask
hand.
another
Yes,
question.
yes,
Somebody,
yes,
there is no one is going to ask.
yes, please.
In the vehicle, ground vehicle, is it possible to tune the vibration level using vibration absorber, or is not possible?
You mean the vibration coming from the road, the level of vibration coming from the road? Maybe I have not understood properly your question.
Yes, sometimes if you have, like, we call it like cabin vibration or driver vibration coming from in his feet, sometimes we can tune, adjust the vibration by using vibration absorbers. Is it possible to do it with the ground vehicle also?
Yes, of course. The overall intention here is to design, or the primary intention of this procedure is to design the suspension of the vehicle to guarantee that you can reduce the level of vibrations for the driver. So under this assumption, the primary intention is to design the suspension, the architecture of the suspension, and also the components of that architecture of the suspension. This is to calculate the spring, the damper, and anti-roll bar or bushings or any other element you need to include in your real world vehicle to guarantee a certain level of comfort.
Thank you.
Thank you very much.
And we have Ayham El Jawabra, please.
Yes, hello everyone. Thank you for your presentation, and thank you again, Ms. Dr. Ahmed, for this workshop. My question regarding you showed in your slides a model on semi-drive line on MATLAB and Simulink, and I would ask a question regarding the parameter estimation. Usually we try to take a measured signal from the system we are analyzing and try to estimate the parameter based on the developed model like the one you showed. My question specifically related to the powertrain torsional vibration, even it was not the topic of the presentation, but more or less it's related. So I would ask, sometimes you have a torsional vibration for the model that comes from the elastic elements, and we may have 3 or 4 degrees of freedom and many springs and mass springs and dampers model, but it is not easy to estimate all of these values. Sometimes we try to estimate this value, but we don't obtain, let's say, a true value. Maybe it will be close, but cannot model the real system. So in this case, what do you suggest that we can do? Can we separate the effect of each component in the powertrain by itself according to the frequency or anything else, or it will be the problem with using a linear contact, linear spring damper system? Thank you.
Hello, sorry.
Mr. John?
Sorry, I lost the connection for a second, but I think I heard all the question. Can you hear me?
Yeah, sure.
Yeah. So sorry, you said the last part I could hear was that how can we overcome the lack of knowledge over the real value of our parameters? Am I right?
Yes.
Good, perfect. So here we have 2 options. If you have access to the real system, you can compute an experimental transfer function. So, for example, imagine you have your engine, you have your drive shaft, and you have your output. You have some action at the end. If you place one accelerometer in your engine and you place one accelerometer in the output of the drive chain, you activate the system, you measure both vibrations, and you compute the transfer function between those two signals. That is your experimental transfer function. So if you do that, now you can do a parameter estimation with MATLAB Simulink to match that experimental transfer function with your model. So what you will do, you will identify the value of your components for your real dynamical system. If you don't have access to the real system, what you have to do is you need to establish, let's say, an objective function. For example, if we are talking about vibrations, you need to establish an objective for the natural frequency and compute the frequency response function inside MATLAB Simulink. So you can do the same. You can take the signal of the output of the input. You can take the signal of the output. You can do a linear system analysis and compute the numerical frequency response function between those two signals and perform a minimization error process to place the peak of the natural frequency, for example, the torsional natural frequency of the axle, to place it in a particular frequency. And if you perform that process and you place your peak on that decided natural frequency, you will have identified the value of, for example, the torsional stiffness of your axis.
So thank you. Hope the question has been answered. Any other questions, please raise your hand or just open your mic. I'm seeing that Professor Ahmed is raising his hand.
Yeah, thank you, Sarah. I don't know if you hear me the availability or how much maybe expensive if the license for the software.
Sorry, I lost the I can barely hear you. Sorry.
Yeah. Okay. My questions about the software. The software, is it free available or it is with a license? And if it is with a license, how much costs the license for educational purposes, if you know?
Yeah, it's a license program. It's a license program, but it's a license program, and we pay 2,000 euros a year, 2,000 euros a year to be used for educational purposes. What it's really interesting is that this is the reference software used by industry, and it has a discount up to 85% of the real cost for universities and for vocational training centers. So it's quite cheap for the capabilities it gives you, and it's accessible for educational purposes.
I see. Okay, so thank you. Maybe some other colleagues have any questions in the last few minutes that we have.
Yes, so let us receive the last questions here, please. Anyone have a question, please go ahead with your question. So I think that it's all clear. Let me take the chance to thank University of Deusto, especially Mr. John and Sarah from the University of Deusto for their great efforts to having this impressive workshop. I just want to remind you all to evaluate our workshop through the link that have been sent in the chat. Your evaluation is highly appreciated. And I want also to remind you that we have attendance sheets for you all. It will be circulated within 2 weeks from this workshop. I will give now the final word for Professor Ahmed Salaime, the coordinator of EcoCar project.
Yeah, thank you, Sarah. Thank you for moderating the workshop, and thanks for Dr. John and also for his colleagues from Deusto University. Yeah, this is maybe for our colleagues that will have, like, as we promise you, that one workshop every 1 month for 2 hours. And hopefully that next year we'll have also some workshops which should be conducted physically in Jordan. And as Sarah mentioned, that please don't forget to evaluate this workshop, and the certificates for those who would like to have it. It will reach within 2 weeks. Thanks again, and wish you like a nice evening and a nice weekend, and see you in the next workshop.
Thank you, Dr. Ahmed. Thank you. Thank you, John. Thank you.
Thank you very much to you all. Thank you very much.
Thank you
Thank
for
you.
all of you,
Thank
and
you.
have a nice weekend.
Bye-bye. Thank you.
Dr.
Thank
Bye
you.
bye.
Thank you. Bye-bye.
Bye bye.
Bye, Engineer Sarah. Thank you very
Bye.
much.
Thank you. Thank you.
Congratulations for your job.
شكرا جزيلا. Thank you.